Any questions that come up during the break on this? How long do you think we sort of known this? That there's a natural greenhouse effect, that it's actually gases in the atmosphere that give rise to this. Any ideas? If you would guess, what would you guess? 50 years? About, yeah? More guesses? Yeah. 49 years. Yeah. So one of the first to suggest this was a French mathematician, Fourier, I forget his first name, in sort of the beginning of the 19th century. So he actually did pretty much what we did with our simple, this bare rock model. He sort of calculated what he knew, sort of you could measure how much energy that came from the sun and calculate what would should the temperature of the earth be, because you knew then about infrared radiation. And he realized that the temperature of the earth would have to be like minus 20 degrees. So then he realized that there's something missing in the picture. And it could either be that we got energy from someplace else, or he proposed that it could be something like a blanket that actually prevents this radiation to leave the earth, that heats up the earth. And one of the first to then actually test this empirically was an English researcher called John Tyndall, which was I think in 1859, that actually emitted or measured how much radiation, infrared radiation, that passed through like a test tube with different gases. So he tried with oxygen and nitrogen, because of course those are the common compounds in the atmosphere, and he didn't get any effect at all. But then he's also tried with carbon dioxide and methane, and saw that it was a strong effect. So that the natural greenhouse effect is not something that is very recent. If you're interested, I can recommend this book, which is called The Discovery of Global Warming by Spencer Worth. It's a really good account of the sort of scientific history of around global warming. One of the first people to actually suggest that humans could change the temperature of Earth and increase temperature by adding greenhouse gases to the atmosphere was a Swedish scientist called Svante Arrhenius in the 1920s or so. So he actually sat down and did sort of hundreds of thousands of calculations to try to estimate what would be the effect if you would double the carbon dioxide concentration in the atmosphere. And we'll get back to this at the end of this lecture as well, to make a first estimate of that. Okay, so now I hope you have a sort of a basic understanding of the natural greenhouse effect. So now we'll start moving into what can change this. So what kind of changes can affect climate through affecting the radiative balance here, the natural greenhouse effect? So any ideas based on this, what we know now? What will change the temperature of the Earth here? We already talked about increasing greenhouse gas concentration, right? Changing this, how much radiation that is emitted back, reflected back into space will also have an impact. Or changing this, changing how much solar insolation reaches us will also have an impact. So you can summarize this into a concept that is called radiative forcing, which is a measure, in essence, it's a measure of an energy imbalance. So radiative forcing is a change in net irradiance at the top of the troposphere, holding surface and tropospheric temperatures constant. I'll come back to that. And net irradiance here is sort of, is measured as incoming solar radiation minus outgoing radiation, which is reflected solar radiation, and outgoing infrared radiation. So think about this picture, and thinking about sort of, you put a a lid here, and then you measure, okay, how much energy is coming in the form of incoming solar radiation, and how much goes out again in terms of reflected solar radiation and in terms of outgoing long-wave radiation. So if radiative forcing is 0, we have energy balance. But if we change one of these, we have an energy imbalance. We are either increasing the energy in the system, so adding energy to the system, which would raise temperature, or we are sort of tapping energy from the system and thereby reducing the energy in the system, or reducing temperatures. So the reason this says holding surface and tropospheric temperatures constant is that, well, what happens if we allow temperatures to change here, which will happen, of course, if we add greenhouse gases to the atmosphere, temperatures will go up. And what will happen then? Well, you'll reach a new equilibrium, right? Where again, so what happens if we sort of we dirty these atmospheric windows, so less emission radiates out? Well, then temperature goes up, which means that radiation will increase. So in the end, temperature increases so much that again we'll emit the same amount of infrared radiation here. So this is radiative forcing is a measure of the energy imbalance we create before we allow the system to sort of reach a new equilibrium. Does that make sense? So radiative forcing results from changes in incoming solar radiation, changes in albedo, which will affect how much solar radiation that is emitted, reflected back into space, and changes in outgoing infrared radiation. For example, due to changes in greenhouse gas concentrations. So this is a picture from the latest, and I'm sorry I forgot to write this, the source here, I should do that. So this is from the latest Ipcc assessment. How many people know what Ipcc is? Most of you. So the Ipcc.
I know too well.
So the Ipcc is short for the Intergovernmental Panel on Climate Change. So it's an international body that gathers scientists that are working with different aspects of climate change, that every now and then, with a few years in between, try to sort of summarize and assess what we know about climate and climate change and its impacts. So there are 3 working groups in Ipcc. There is the working group 1, which is the scientific basis. There's working group 2 that looks at adaptation and impacts. And there's working group 3 that deals with mitigation, so possibilities to reduce greenhouse gas concentrations. So the first Ipcc assessment came in 1992, if I remember correctly, and there was one in I think 95 as well. There was one in 2001 and there was one in 2007. And the latest one, from working group 1, the latest one came out just this, I think, in December. So this is from this assessment. So this is measures of radiative forcing divided up to different drivers of radiative forcing. So this is all measures of this energy imbalance. So on the top you have carbon dioxide, radiative forcing of, in total of about, see, what is it, 1.7 or 1.6, oh, it says here, 1.68 watts per square meters. So radiative forcing is measured in the same unit as we have here. We have incoming solar radiation in watts per square meter, we have reflected solar radiation in watts per square meter, and we have outgoing radiation here. So radiative forcing is measured in watts per square meter. So the biggest influence on radiative forcing in terms of greenhouse gases comes from carbon dioxide. Then we have methane. And for methane, it's divided up to, so for methane in itself is a strong greenhouse gas. That has a direct impact on radiative forcing. But methane also have important indirect effects. So increases in the concentration of methane in the atmosphere affects the chemistry in the atmosphere. And one thing it does is that it increases the level of ozone, tropospheric ozone. in the atmosphere or in the troposphere. And ozone is also a very potent greenhouse gas. So therefore, this increase in ozone that is due to the increased level of carbon dioxide, or methane, is attributed to methane here. And another effect is that it increases as some of the methane reaches the stratosphere, and there it's broken down quite quickly by this shortwave radiation, and turns, the methane, the hydrogen goes into forming water vapor. And water vapor, again, is also an important greenhouse gas, so that also adds to the warming. Then we have these halocarbons, so the CFCs and HCFCs, which are also important, and nitrous oxide. And what you have here on the negative side is actually the reduction of ozone in the stratosphere, so ozone depletion. And why? Can you have an idea why that is a negative radiative forcing? Less ozone in the stratosphere? What is the result of the ozone depletion, ozone hole? Yeah. So there's more shortwave radiation reaching the Earth's surface and warming it, instead of being absorbed there and then remitted out into space. So that's why less ozone there actually implies a warming. So less ozone, or less ozone in the stratosphere. Sorry, I think it feels like I'm messing things up here. Yes, I'm messing things up. Sorry. So it's a cooling. It's the same here. That there's a cooling because you have less ozone, and ozone is a greenhouse gas. Should be. So it's a greenhouse gas in both areas. Sorry. Then we have short-lived emissions of short-lived pollutants. So carbon monoxide, non-methane volatile organic compounds, and NOx, so NO and NO2. And those are not direct greenhouse gases as these other greenhouse gases, but they also contribute to changing the chemistry of the atmosphere, and thereby affecting the concentrations of other greenhouse gases, carbon dioxide, methane, and ozone. How does it have a cooling effect? Okay, but that has more. So that's just a sort of a redistribution of the energy in the atmosphere, and does not constitute a complete cooling. So the main effect that changes in water vapor has on the temperature is through being a very strong greenhouse gas. So increases in water vapor means more infrared radiation being absorbed, and therefore a stronger greenhouse effect. What you'll talk about on Friday when it comes to climate feedback, and you'll also see tomorrow, is that it's not human emissions of water vapor does not affect the concentration of water vapor in the atmosphere. However, what happens as the temperature goes up is that the atmosphere's ability to hold water vapor increase, and therefore water vapor increases, and and you have a feedback effect there. So these are all changes in radiative forcing due to changes in outgoing infrared radiation. So more absorption from higher levels of these different greenhouse gases. Most important one, carbon dioxide, and then methane. Then what you have here is things that affect the albedo, so the share of incoming solar radiation that is reflected out into space. So here, one important part is aerosols, and it's hard to see here. It says mineral dust, organic carbon, black carbon, and so on. So black carbon is warming because it absorbs the incoming solar radiation, especially when you have aerosols. So these particles that ends up on white surfaces like snow and ice and so on. It changes the albedo of that the snow and ice very much. But the other aerosols tend to reflect solar radiation. So sulfur particles, for example, tend to reflect the incoming solar radiation and increase the albedo, which has a cooling effect of the climate. And then you have one important effect, which is changes in clouds due to the presence of aerosols. And you see, you have the sort of point estimates, but you also have the uncertainty range here. It also says out here level of confidence, so VH is very high, H is high, and so on. And one of the big uncertainties in our understanding of the current climate and how it's affected by human perturbations is how aerosol emissions affect cloud formation and how that in turn affects the radiative balance. That's a really good question. I would expect that it's a combination of sort of empirical data and model data that's behind this, but I'm not sure. But so one reason why there is such a big uncertainty here is sort of one way to try to estimate these things are through these global circulation models, as they are called, global climate models. But they have quite a coarse resolution. Daniel will talk more about this. So they are not very good at capturing these cloud formation mechanisms that happens at the scales of micrometers or something. And they have a resolutions of hundreds of meters or kilometers. So one reason why the uncertainty here is that the models are not very, very good. Then we have changes in albedo due to land use change. So primarily deforestation. So bare earth tends to have a higher albedo than forest or vegetation. So as you clear land, more of the radiation is reflected out into space. And then finally you have changes in incoming solar radiation here. So you actually see an increase in the solar activity. So, and this is sometimes brought up as isn't global warming due to simply the sun being more active? And yes, you see an increase in solar activity or radiation from the sun, but compared to the other things that are happening in the system, it's very, very small. So here you have total anthropogenic forcing from compared to 1950, 80, and 2011. Keep track of time. So one of the questions you had, we have for the oral exam, concerns the effect of land use change and albedo. So the question is, forest clearing in the non-tropics released 250 billion tons of carbon dioxide to the atmosphere in the period 1850 to 2005. The net climate effect of this deforestation was a slight cooling. So how can this be? Because emissions of greenhouse gas or carbon dioxide was so big. So something must have counteracted that. So what was that? The increase of albedo, exactly. So you replace these forests with agricultural land. So what this graph shows, first I should have said it. So this is land use change. This is carbon emissions from fossil fuels, from land use change in the non-tropics and in the tropics. So you see that it was only until the beginning of the 20th century that fossil emissions actually were higher than the land use change emissions. And most of that was in the non-tropics. So today the focus in the climate debate is about deforestation in the tropics, but historically we in the northern latitude has been no better at preserving our forests. So here you see one study that looks at the effect of this deforestation historically. This is the net effect, the dark line here. This is the effect if you just account for the carbon dioxide emissions from this deforestation. And this line is the effect if you only account for the changes in albedo. And the reason why it's it's a big effect from deforestation, cooling effect from deforestation on northern latitudes, is the changes albedo is even higher, because in the winter, if you have bare ground that is covered by snow, it has a really high albedo compared to a forest. So this effect is stronger in the northern latitude than it is in the tropics. So you see a change in albedo in the tropics as well, but it's not as big as it is in the northern latitudes. So net cooling. So if you start to reforest in the northern latitude, and you think you're doing something that is good for the climate, it's not at all obvious that that is the case. There's a PNAS paper that looks at sort of, so this is the historic, but looks into the future and looks what happens if we cut down like all the forests all the boreal forests, or all the forests in the tropics, or all the forests in the world. What effects does that have on the climate? So even if you would cut down all the forests in the world, the net effect of global average temperature would still be a cooling, actually. But geographically, there are large differences as well. I don't have it at the top of my head, but you're completely right. So replacing the forest with cropland, for example, affects the albedo. It has effects on greenhouse gas emissions, and it affects evaporation or evapotranspiration. So how amount of water vapor. And in this PNAS paper, they account for all those three effects, and those effects kind of look different in different depending on where on Earth you are. So deforestation in the tropical areas are still contributing to climate change. But the net of these effects in boreal areas of deforestation is actually still a cooling. But I can't remember exactly how, but I'll look up the paper and send it to you, and you can read about it there. But it's just, here's more to illustrate that albedo changes have an important effect. But yeah, don't take this to mean that it's fine to cut down the forest of the earth and so on. Especially in the tropics, avoiding deforestation has a positive effect on the climate. But it's not, but it's also important to remember that it's not obvious that reforesting in Sweden, for example, actually has a positive climate effect. Okay. What we'll do first, actually, is, so one of the exercises you had for today was actually to estimate radiative forcing in this simple model we had, right? So we'll do that. And how much time we have? I'll just draw if I remember the one here. So the first question was actually to estimate. We had in our model, we calculated that the emissivity of the atmosphere was 0.773, right? And the question was, what happens if we increase that by 0.019, which would be sort of equivalent to a doubling in this model of carbon dioxide concentrations. So radiative forcing we just said was the change in net irradiance at the top of the troposphere. So here if we so what's the net irradiance? And actually what we can do, the only thing that changes here, so if we change the emissivity of the atmosphere, we won't change anything that has to do with the incoming solar radiation or what is reflected out again. So we can just disregard from that. So what changes is actually only the outgoing infrared radiation here, right? So we can calculate this. So what we have, and I'll put numbers now directly. That's okay. So we have 1 minus the emissivity of the atmosphere, 0.773 to start with, times 5.67, 10 to the power to minus 8, times the temperature of the Earth, the surface, which was 288 Kelvin to the power to 4. So this is this part, right? And then we had 0.773 times 5.67 to the power to minus 8. Can you see here now? Times 242 times 2 power to 4. So this is this. The emissivity of the atmosphere times sigma times the temperature of the atmosphere, which we knew from before was 242.2 degrees Kelvin. So that's our initial state, the outgoing infrared radiation. And now we want the change, so we subtract what we get once we increase this. So again, we have 1 minus, now we have 773 plus, oh sorry, minus 9, yes. What's their question? Paul? So now instead of having E, the emissivity of the atmosphere being just 0.773, we have 0.773, and then also, so we increase this. Okay? And then the same thing again, 5.67 times 10 to the power to minus 8 times 288 power to 4. Let's see if I can pull this out. And plus the new emissions from the atmosphere, which is 0.773 plus 0.019 times 5.67 10 to the power to minus 8 times 242.2 to the power to 4. And if you write it into a calculator or Excel, you'll get 3.7 watts per square meter. Is that clear? So what we calculated is just how does the outgoing infrared radiation here change as we increase the emissivity of the atmosphere.
Why did you change it by 0.019? Was that corresponding to?
That was because I know that the radiative forcing from a doubling of carbon dioxide concentration is 3.7 watts per square meter. So in our model, a doubling of carbon dioxide concentrations is corresponding to this. But there's since this is a very simple model, it's sort of, I tuned it so it gives the same results basically as something more complex. So thinking about what you asked yesterday, Laura, about sort of, okay, these watts per square meter, what does it actually say? You can think about this. So this is not very much, right? This is not even adding a light bulb per square meter. So it's not very strong. So what effect will this have on the temperature? That was the next question. So how does the average temperature in this model, the equilibrium temperature? So this is the change in outgoing infrared radiation when you hold the temperature constant there. Look, so we have 288 degrees Kelvin here. It's the same before and after. So we have not reached new equilibrium. The temperature is still the same, both for the surface and for the atmosphere, right? Yeah. Oh, that's good. That's a good question. So this is from going from 280 to 560 ppm. If you double it once more from 560 to 1120 ppm, what do you think would happen with this then? That's, you will look at the lab tomorrow. So that's precisely the question. So if you double it once more, will that, how is there a difference? So you will look at what's the relationship between radiative forcing and increases in different greenhouse gases. And it turns out it's not the same for all gases. Can I erase this? So the next question was to calculate something you can call the climate sensitivity. So if we increase the emissivity of the atmosphere in this way, okay, if we let this go to a new equilibrium temperature, what is that temperature? How much does the temperature increase to compensate for the fact that more of the radiation now is absorbed in the atmosphere? So we need to increase the temperature here so that in the end we again release the same amount of energy out to space. So just to remind you, we have in this system we have the energy balance of the surface. We can express as 1 minus alpha I sun divided by 4 plus E at sigma T at 4. So the incoming solar radiation that is absorbed plus the back radiation from the atmosphere that is absorbed must equal what is emitted out to space, which is sigma T Earth to the power 4. Then we have again the energy balance of the atmosphere, which is E at sigma T Earth 44 equals 2 times E at sigma T at 4. So in the atmospheric layer, the incoming energy is what is absorbed of the radiation from the surface, and then that must be balanced by the outgoing radiation. So the radiation goes out to space and the radiation that is back to the surface. So from that we see that T at 34 equals T Earth 34 divided by 2. As before.
Where does the 2 come from?
This 2?
Yeah.
It comes from basically from the fact that the atmospheric layer radiates both back, up and down. Right?
That's why doesn't it radiate sideways as well, or why is it just like that?
Well, of course, but that is still then inside our layer here, so it's just it doesn't matter. It doesn't. The energy then does not leave. Yeah, but of course, this is simplification. It's the atmosphere. It's something like this, which is reality is more, of course it radiates in all directions and so on. But in our simple model, that's how it works. Well, if we plug this into this equation, we have 1 minus alpha I sun divided by 4 plus emissivity of the atmosphere, sigma, and then instead of writing T at there, we write T Earth power to 4 divided by 2. And again, that equals sigma T Earth power to 4. We solve this for T Earth, and I won't do the details now because we did this yesterday, but if you want to go through it yourselves, you can do it. So T Earth is the fourth square root of 1 minus alpha I sun divided by 4 divided by sigma minus E at times sigma divided by 2. So we know the numbers for I sun. So alpha here was 0.3. The intensity of the sun was 1368 watts per square meters. Sigma is just a constant. So if we use the first number so if we use that the emissivity of the atmosphere is 0.773, we get T Earth equals 288 Kelvin, right? That's what that was in the assignment. So we've done, then we know we've done something right. If instead we assume that EAT is 0.773 plus 0.019, we get T Earth equals 289.2 Kelvin. So the difference in T temperature here is about 1.2 Kelvin. So if we do something in this model here that corresponds to a doubling of carbon dioxide concentrations, the increase in average temperatures is 1.2 kelvins or 1.2 Celsius. Same. That's a good question. So if a doubling of carbon dioxide concentration, so we're not at a doubling yet, increases temperature by 1.2 degrees Celsius, why do we talk about it so hard to go below 2 degrees Celsius? So this is a measure in this simple model of the climate sensitivity. What does this measure miss compared to the real greenhouse effect and the real? Thank you. So feedback effects. Yeah, exactly. So this does not account for example, as you said, changes in albedo. That will change, that will increase warming. It does not account for increases of water vapor as the temperature goes up and so on. So this is a lower number than the real number. So this is just what occurs so what is needed for the radiation balance to be restored. But then you have all these effects on top of that. And that Daniel will talk about. Great. Let me just quickly, because we have a couple of minutes, and I want to at least show you the idea of how we compare different greenhouse gases. And we can do this really quick. So how do you compare emissions of different greenhouse gases that both have different strengths? So shows the radiative forcing relative to carbon dioxide per kilo of emission. So if you emit 1 kilo of methane, the effect on the radiative forcing is about 60 or 70 times as high as from emitting carbon dioxide. For nitrous oxide, it's 200. And as you see, for these compounds that are not normally found in the atmosphere, that absorb really well in this atmospheric window, they are really, really strong greenhouse gases. So the effect of on the radiative forcing from emitting 1 kilo of this sulfur hexafluoride is 10,000 times as big as from emitting 1 kilo of carbon dioxide. So they're different in strength, but they're also different in their lifetime in the atmosphere, how long they persist in the atmosphere. So methane is quite short-lived and has an average lifetime of only 12 years, whereas nitrous oxide has a longer lifetime, 120, and SF6 has a lifetime of 3,000 years. Persists for a very long time. So the way you do this, and for carbon dioxide there is no number here because there's not a single lifetime, but so some of the carbon dioxide actually disappears from the atmosphere. This is the blue line here. So you're comparing the fraction that remains in the atmosphere as a function of time in years here. So quite a large fraction of the carbon dioxide that gets emitted is absorbed mainly by the oceans quite fast. But then you have a share of the carbon dioxide emissions that remain in the atmosphere indefinitely. So around 20% of the share. And this Daniel will talk more about tomorrow. But so you have these different lifetimes or how it disappears from the atmosphere, and you have different strength. And the common way to do this, and I just want to give you a sort of an idea what this means, because one thing you will come across is something called the global warming potential, which is the common way to compare emissions of different greenhouse gases. And what the global warming potential does, it compares the integrated effect of radiative forcing under a certain time span with that of carbon dioxide. So this is the increased radiative forcing for an emissions of 1 kilo of methane. And here you have both the direct effects and the indirect effects. Compare that, so you see you have a strong effect that decreases quickly over time. Comparing that with carbon dioxide, which has a longer lifetime. So there's a difference in scale. So the total effect here, when the emission occurs, is about 100 times bigger for methane. But much of that disappears quite quickly. So what you do in the global warming potential is you integrate this. So the cumulative radiative forcing under a number of years. And you compare that with the cumulative radiative forcing of an emission of 1 kilo of carbon dioxide. And then that ratio gives you the global warming potential. So carbon dioxide has a global warming potential as one. That's the sort of the norm against what you compare. Methane, so it's a stronger, higher impact of radiative forcing, but it has a much shorter lifetime. So especially if you look over 100 years, you get a global warming potential for methane of 28. So emitting 1 kilo of methane has the same cumulative effect over 100 years on radiative forcing as emitting 28 kilos of carbon dioxide. For nitrous oxide, 200 times stronger and has quite a long lifetime, so over 100 years, it's about 265. SF6, see, very strong and has a very long lifetime. So a global warming potential of 22,000. So I'm emitting 1 kilo of this gas has the same effect of radiative forcing over 100 years as emitting 22,000 kilos of carbon dioxide. CFC, strong greenhouse gas, but a shorter lifetime, so a little bit lower. So this is, but if you compare effect of radiative forcing over 20 years instead, well, then you get a much higher global warming potential for methane. Because then more of this methane is actually left in the atmosphere. So this is the most common way to compare emissions of greenhouse gases. And sometimes you see emissions in carbon dioxide equivalents. And then you take in, for example, emissions of how many X tons of carbon dioxide plus Y ton of methane times 28 plus Z tons of nitrous oxide times 265. And then you have them on a sort of a common metric. And so that's what meant when it says carbon dioxide equivalents. So it's good to know, at least have a sense for what this means. So it's the effect of radiative forcing over time, the cumulative that you compare. But that is not the same thing as effect on temperatures and so on. So there are a host of other metrics. There is one that is being used more that is called the global temperature potential, which looks at, okay, if we emit 1 kilo of carbon dioxide today, how much does that increase temperature, global average temperatures in 100 years' time? And then you compare with 1 kilo of methane. And then you get a slightly different number. So there are different metrics, proposals for metrics. But this is the one that's still most commonly used. Yeah, so this is sort of arbitrary. And there are people that have written about sort of the political science and things about, so but basically so this is a long-term problem. Let's see what the effect is over 100 years. 20 years is too short time, and so choosing 100 years does not have, there's no scientific basis of choosing 100 years over 20 years. So. Yeah. Okay. So, quick summary. Main contributors of the natural greenhouse effect: water vapor and carbon dioxide. Those are the most important natural greenhouse gases. Oh, I didn't talk about this really. I didn't say it, but you'll do it in the lab tomorrow. That as absorption from greenhouse gas becomes saturated, radiative forcing will not increase linearly with concentration. So you see, that's what I talked about, was that you get this broadening, and it's not as effective as the absorption in where it absorbs best. And you will look at this in the lab and actually quantify this for these different gases. And then remember what radiative forcing means. So it's a change in net irradiance at the top of the troposphere. So it can result from changes in solar irradiance, changes in albedo, and changes in outgoing radiation. And what is it is a measure of is an energy imbalance. So with the radiative forcing you saw in the graphs from Ipcc, that's a measure of how much extra energy is pumped into the Earth's system, heating it over time. And then we just showed you briefly the common way to compare emissions from different greenhouse gases, which is this global warming potentials, which is an integration of the radiative effect of emission of 1 kilo of the gas over a certain time frame and comparing it with carbon dioxide. Thanks.